We're getting quite close to the end of our journey here on TensorFlow on the Google Cloud platform. So let's very quickly take stock of where we stand. We began with some introductory steps, just getting set up on the Google Cloud platform. We got set up with Data Lab, which is the Python IDE. We pulled a bunch of data from a public data set in BigQuery. Then we instantiated an estimator object. And by this point, we were thoroughly within conventional TensorFlow land. We added a level of indirection by making use of the experiment framework, which is available within tf.contrib.learn. This is a harness for training and validation and for serializing the best model that we end up with. Steps 2 and 3 of this process did not involve the cloud at all, but that changed in the next step, which is where we made use of ML Engine, that's Google Cloud Platform's offering, for distributed training. We carried out training of our TensorFlow model at scale on the cloud with a large dataset. Once we were done training, we made use of another service also provided by ML Engine, and that was the prediction service. That gets us to where we stand right now. We have built a model. This predicts the fare for a taxi cab trip in New York City, and we have trained this model in a distributed manner on the Google Cloud platform. We have also experimented with using this model for prediction, once again from the Google Cloud platform, making use of the ML engine. We are now going to tweak our model. We are going to effectively rebuild this model from scratch with a new set of X variables. We're going to make use of something called feature engineering. This demonstrates smart ways of combining the X variables using TensorFlow's functionality. And as we shall see, feature engineering will substantially improve the performance of our model. So let's get started and let's very quickly pick up from the first step in our process. This is where we loaded the schema of a public data set from BigQuery. We had said at the time that we will remove some of the columns that we are not going to make use of. And it was also our plan to filter and clean that data, all of which makes complete sense. Specifically, in our first iteration, we had said that we are going to ignore the date and time of the pickup. That is going to change now in the new version of the model that we are about to build. We will reintroduce this variable. While doing so, we will do something interesting. We will consider the day of the week and the time of the day together as one combined feature. That's a tuple. And along the way, we will make use of two types of layers made available to us within TensorFlow. The first is called a sparse column with keys. This is something that we will use for the day of the week. And then a sparse column with integerized features. This is what we will use for the time of the day. Finally, we will combine these using a crossed column. More on all of these terms coming up. We will also make use of a crossed column for the pickup longitude and latitude. Once again, it makes sense to consider these two as a tuple, that is to consider them together. In addition, before we take into account the latitude and the longitude, it also makes sense to bucketize them, because really we don't care about the fifth decimal place in either of those two quantities. We would like to discretize them and just get a coarse sense of what the lat and long are. So with the latitude and the longitude, we are first going to bucketize them and then create a crossed column of the two. And we will do the same for both the pickup and the drop locations. So let's go ahead and get started. Let's get back into the code. Let's navigate to the top of our directory of our source repo. We see there a folder called feature engineering. We click on that. Within that, we find there are multiple IPython notebooks. Let's click on the one called featureengineering.ipynb. The other two deal with hyperparameters and with a new technology called TF transform, which we are actually not going to talk about in a lot of detail. Let's open up that feature engineering IPython notebook, and a lot of what we see initially ought to look pretty familiar. We will start by setting up a bunch of environment variables. Note that we have to customize our project, bucket, and region. This obviously makes sense because we're going to need these environment variables in order to communicate with the Cloud ML Engine service. We also need to customize the path of the repo directory so that it correctly mirrors the place where we cloned the Git code. Once that's done, we go ahead and run ls and make sure that we do indeed get a successful directory listing. Notice that while doing so, we made use of the os.listdir method. We could also have made use of a bang ls command to interact with the bash shell directly. In any case, let's move on. Let's correctly set the values of some environment variables so that our bash shell will be able to work as we want it to. So we've got to specify the project, region, repo, bucket, and so on. With that done, let's now turn our attention to the query which pulls the data. Notice that as before, we have a create query method, but we now modify this method so that it actually returns the day of the week as well as the hour of the day. And once again, this is something that we do making use of BigQuery's built-in date and time parsing functionality. So day of week and hour, that's all that we need. Let's keep moving on. We run this function. As usual, we do so by invoking the create query function. This takes in two parameters. The first is the phase. Here, the phase is validation, and so we enter phase equal to 2. And the second is the sampling proportion, which here once again is 1 of every 100,000 rows in the original data. We go ahead and execute this, and we see that we have successfully gotten the data back. The folks at Google who put this code together have very helpfully included a line there. That line tells us that we can try the query directly for ourselves in BigQuery. It does recommend that we add a limit 10 because obviously this is going to pull a lot of data. And so if we are going to run this query interactively, we do not want to sit around waiting for hundreds of thousands of rows to come back.